In this video, I'm going to show you 10 essential data structures that will change the way you solve problems. Let's fill your toolbox. Arrays are simple, but 80% interviews start with them. The most powerful patterns like two pointers and sliding window all operate on arrays. The greatest strength of an array is that it stores data in a continuous block of memory side by side. This allows the computer to know exactly where an element is located, making access by index incredibly fast, constant time access. But this rigid structure comes at a cost. Arrays are not flexible. Their size is fixed at creation, and increasing or decreasing an element from the beginning or middle can be very slow. For example, imagine we want to insert a new element into the middle of this array. To make space, we have to shift every subsequent element one position to the right. This is an O(n) operation, and it becomes very expensive as the array gets larger. And the time complexity of the operation of array for access is O(1), but search, insertion, and deletion, it's O(n). It's linear time complexity. Linked list the flexible chain. This is the solution to the rigid structure of arrays. A linked list doesn't store data contiguously. It stores it in separate nodes that point to each other. So how is this stored in the memory? One node could be in one corner of the memory, and the next node could be somewhere completely different. The only thing holding them together is that magic link between them, the pointer. Adding or removing an element from the beginning or the end is incredibly fast because we only need to update a couple of pointers. This is an O(1) operation, but this flexibility also has a cost. Unlike with array, you can't jump directly to the 100th element in the linked list. You have to start from the beginning and traverse 99 to get to the 100th. This is why accessing an element by index taken O(n) time. Operation of the time complexity of the linked list, access and search is O(n), and insert and deletions from start and end is O(1). Arrays and linked lists store data in sequence. But what if we want to access data initially without following a sequence? That's where the HashMap comes on stage. Think of HashMap like a magic catalog system of a giant library. Every book has a unique catalog number, the key, and this number tells you the book's exact location, the value. This system works with a mathematical magic called a hash function. You give your key in this function, and it gives you the exact address in memory instantly, in O(1) time. You don't need to search even among millions of books. The time complexity for access is O(1). Search and insertion, deletion, O(1) time complexity also. What if we are only interested in checking if something exists and not in the associated value? Think of a HashSet like a VIP guest list at the door of an exclusive party. The bouncer has only the job, is this person's name on the list or not? They don't care about the person's age or job. They only perform an existence check. A HashSet guarantees that every element added to it is unique. This has also happened in O(1) time. The operation's time complexity is for search, insertion, and deletion is O(1). Now let's move on to data structure that process data in a specific order. First stop is the stack. Think of a stack like a pile of clean plates in a restaurant. When a new plate arrives, you place it on the top. When you need a plate, you also take one from the top. This is the last in, first out principle. This structure is perfect for when we jump from one function to another in a program, or when a web browser uses the back button. For example, we create a stack, browser history, and we push google.com, push youtube.com, push Codeviento. So when we want to get the last visit history, it will be Codeviento comes out first. The greatest strength of stack is providing instant access to most recently added elements. However, you can't directly access a pile in the middle or at the bottom. You have to remove the ones on the top of it one by one. Operations of time complexity, push insertion O(1), pop deletion O(1), pick view the top element O(1), search is O(n). The cousin of the stack, which works with the exact operation logic, is the queue. Think of a queue like a ticket line in front of a movie. The first person in the line is the first person to get a ticket. This is first in, first out principle. This structure is ideal for situations that require tasks to be done in the order of their arrival, such as printing jobs sent to the printer. For example, we create a printer job queue, and we send document 1, then document 2, then the document 3 to our printer. When we run the first job on our printer, the first job will be the document 1. A queue provides instant access to the element at the very front and very back to the line. But just like a stack, to reach a person in the middle, everyone in front of them has to leave the line first. The operation of time complexity for offer insertion is O1, pull deletion is O1, pick view front element is O1, but search is On. The data structure we have seen so far have been linear. But we are moving to hierarchical structure, this with a parent-child relationship. The most famous of this is the binary tree. Think of a binary tree like a family tree. At the very top there is a root ancestor, and each person can have at most 2 children, a left child and a right child. The most specified version of this structure is binary search tree, BST, which always keeps its data sorted. Everything to the left of the node is smaller and everything to the right is larger. This makes searching, insertion, and deletion data incredibly fast. The power of trees in organizing data in a natural hierarchy, however, an unbalanced tree can, in the worst-case scenario, behave like a linked list and lose its performance benefits. For a balanced BST, operation time complexity is for access, search, insertion, and deletion is log n. Think of a tree like a structure that organizes the words of a dictionary letter by letter. Each node represents a letter, and you follow a path of letters to form a word. Its greatest strength is checking very quickly if a word or a prefix exists in the dictionary. Let's create a dictionary and insert cat, car, and code to the dictionary. And when we search the dictionary for cat, it will return true. And at the same way, for the carrot, it will be returned false. And if we check with a start with word, it will be true also. The operation time complexity for search, insertion, and starts with is OL. L is the length of the search word. A heap is a special type of a tree with one simple rule. Parent node is always greater than its children in the max heap or smaller than its children in a min heap. Think of a heap like a company organization chart. The CEO, the root node, always has the highest authority, the greatest or smallest value. In Java, it comes to us as the priority queue. Let's create a min heap, and when we add to min heap 20, and then 10, and then 30. And when we try to pick heap, it will return 10, the smallest one. Heaps play a vital role in top key problems, shortest path algorithms. However, a heap only provides fast access to the top element. Searching for an element in the middle is inefficient. The operation time complexity, find minimum or maximum O1, insertion O log n, deletion O log n, and search is On. And finally, we arrive the most powerful and most general data structure, the graph. Think of a graph like a city and route on Google Maps. Each city on this map represents a node or vertex. Each road connection these cities represents an edge. Unlike trees, graphs don't have a strict hierarchy. Routes can be one way or two ways. And you can leave a city following different routes. End up back where you start, these are called cycles. It allows us to solve shortest path problems. Algorithms are breadth first search and depth first search are the methods that allows us to systematically search for the path on this map. For example, we can create a city map, key is the city, vertex, and value is the root of neighbor cities, edges. And we can add our city map to A and B and the C cities. We can add a route exist between A and B and A. A route exists between B and C and B. Graphs are used to model the complex connection in the world. And traverse algorithms like breadth-first search and depth-first search allow us to find the most efficient routes on that map. If you want to see that data structure in action, check out my Amazon interview series right here. Thank you for watching, friends. Don't forget to like and subscribe for more, and I'll see you in the next one.